Alright everyone, welcome back to Cody's Lab. So if you've been watching the channel for a long time, you might remember back during the mining series that I had sent in a sample of the assumed ore in for a professional fire assay. And the assay came back telling me that it was 40% lead. That's a lot of lead. It got me to the point where I was afraid to dig in that mine because I didn't want to be breathing in or even touching the dust. Lead's messes with your brain, and that's one of the things I quite value about myself is my intelligence. So it was one of the things that got me to give up on the project. It wasn't until later that I got access to an X-ray gun and did some other tests of my own that showed that it only contained at most the smallest trace of lead, which tells me that my sample was almost certainly mixed up with somebody else's. Probably somebody with a hunk of galena. And that really messes you up when that happens. You're supposed to trust them. You're spending all this money and the results can just be messed up somehow. And what am I gonna do? Sue them? If I was a big company, certainly, but I'm just a little guy. I probably had an intern do my sample, give them experience. Low risk of legal action if they mess up, But the thing is, it'd be something if that's happened once, but I've caught another company doing it. Similar thing. My dad has had problems. My grandpa had loads of problems with it. He would send samples into 2 different companies and they'd come back with different results, even though it was the same bag of material. It got to the point where he would just do his fire assays on his own. If he just does this rock have gold or not, he could just do it, right? And then if he needed some official documents to show investors or a buyer, then he could send in a sample that he already has a pretty good idea of what it has. So if the results come back wonky, he knows. And I'm getting into the same camp. My problem is, again, the lead. Lead vapors, it's very easy to poison yourself. And so I kind of backed off on it. I haven't done any fire assays on my own in a long time. But I recently discovered you can use bismuth, which is a non-toxic metal. And, the vapors are still toxic, cause respiratory problems, but it doesn't accumulate in your bones like lead does. So I think I'm going to get back into doing some fire assays. And I figured I would bring you guys along, kind of do it in a DIY style as much as possible, so that perhaps if you want to do some fire assays of your own ore to get an idea of what you have before you go through the trouble of trying to send multiple samples to multiple companies and spending all that money, you'll be able to do it. Okay, so here's some samples that I just had on hand. These came from different mines. This one is some quartz that came out of California. This actually is the mother lode of what started the gold rush. This came from a mine in Mercer, Utah. You see, looks pretty good. Looks like it got loads of gold, but that's actually iron pyrite. Now, it probably does contain some precious metals. Just because it's called fool's gold doesn't mean it's not valuable. It's just not, solid gold. And this is just a piece of calcite that I picked up from somewhere that looked pretty good. See here. So basically what we have is a carbonate ore, a sulfide ore, and a silicate ore, so different chemistries. So now that I have my ore, the first thing I need to do is crush it into a fine powder. It doesn't have to be like baby powder sized or anything, but if it can go through a fine mesh screen like this, that's probably good. So what I'm going to be using to crush it is this 6-inch pipe cap with a locker door welded to it to help keep the pieces from flying out. And for my pounder, to actually do the crushing, I've got an old axle. So just crush the ore like this. You'll see I'm doing this outside next to a fan so that I'm not breathing in the dust. Fan works great for keeping the dust away from me. That's especially important if you're doing a silicate rock. Silica is carcinogenic, cause you lung cancer. So now that I've crushed this down a little bit, I'm getting to the point where the smaller stuff is cushioning the big stuff, making the crushing go slower. So I'm going to pour it out into this screen, just like that, and sieve it through. This gets rid of the smaller stuff that's cushioning the big stuff. Okay, now the small stuff sift out, put the big stuff back in the crusher bowl. And turn my fan back up, continue crushing. Okay, so that's all crushed. There's a few bigger pieces left in the screen here. Just want to give those a quick once over to check for nuggets. If you found a gold nugget here, it'd probably be smashed into a flake. But you'd want to split it up with whatever fraction of the material you're actually using for the assay. Like if you're only going to use half the crushed powder for the assay, you'd want to cut the nugget or flake in half, you know, so it's representative. Now, these larger pieces, those will be fine. Just put them in. But my next task is to thoroughly clean the crusher bowl. I've got some abrasive wool here to kind of scrub out the last of the powder that's stuck to the bowl. There we go. I'd probably hose this out, maybe scrub it some more. I really don't like this bowl because it's got loads of little places where stuff can get caught. And if something gets caught in here, it'll end up in your next batch as cross-contamination. Also, to help knock out any potential material, I'll also crush up some pieces of something that doesn't have any values in it. This is just some marble chips. Crush those up between samples to help dislodge anything that's caught in the bowl, to help with the cross-contamination. For now, let's get this transferred into a container. Like so. There's my crushed ore sample. See, I've got the container labeled. I don't know if you can see that. Let me see if I can zoom in. You see? Come on. You can see the sparkles, pyrite in there. Okay. Now that my equipment is clean, got a new piece of cardboard, time to crush up another sample. That's pretty good. Here are the ore samples, crushed into a fine powder. Now the silicate ore, it's good to go. I can put that in a crucible with some flux and do the assay as is. The other two, however, are going to have issues, so it's going to require another step. The carbonate, for example, the calcium carbonate is going to decompose upon heating, releasing carbon dioxide gas. And all that gas coming out is going to cause the assay charge to froth and boil over and make a huge mess. The sulfide ore, the metal sulfides, those are very difficult to dissolve in the flux. So that's going to trap your precious metal particles. But also the sulfides are a reducing agent which is going to mess with your chemistry. Fortunately, both of those can be solved by pre-roasting the ore. So we've got a ceramic bowl here, labeled. I'm going to set it on a scale, just like so. And now I'm going to put in 60 grams of the crushed ore. Yeah, perfect. Kind of spread that around so it's got a high surface area. And I'll do the same for the sulfide ore. And I may as well do it with the silicate ore also. Doing this pre-roast isn't going to hurt it. So to roast the ore, I'm going to be putting the bowls down at the bottom of my pottery kiln here. I'm recycling the kiln to cone 06, which is about 1,000 degrees Celsius, which is a little hot. It only needs to go about 700 degrees Celsius, but as you can see, I'm going to be cooking some other stuff at the same time, so we go a little hotter. It's not going to really do any harm to it. Still well below the melting point of silica, so this is going to do pretty much nothing. Might lose a little bit of water if there's any there. The carbonate ore, the calcium carbonate, is going to decompose into calcium oxide or quicklime, releasing the CO2. It's going to be doing it now rather than later, which is exactly what I want. And the sulfide ore, the metal sulfides, are going to essentially burn in the extremely hot air. So it's going to release sulfur dioxide and leave the metal oxide behind, which is much easier to work with. Now, note on that, if you've got something with a lot of lead in it, such as this piece of galena and pyrite, it's actually a two-step process for lead. The oxygen takes off the sulfur, leaving behind metallic lead, which then has to further oxidize. And if the lead particles are too close together, then they'll coalesce and then sink down to the bottom, where it's very difficult to further oxidize. So you want to kind of spread it out so the oxygen can get to all the lead particles. So you'd want to like mix it with something fluffy like silica sand or something. Also, you don't want to get it hotter than the melting point of the oxide. That's not a problem for the iron, but lead, that would be, and that would make things stick together and be very difficult to remove from the bowl. So anyway, over here I've got some cattle bones, which I'm going to be cooking to bone ash, which we'll be using later to produce the bone ash cupels, which I've got one right there. And all of this stuff here is just me testing out my recipes, make sure everything works before, I'm showing you or doing it at full scale. So anyway, let's close the lid here and cycle this thing through. Let's pull out one of the vents so it can get some air. It's probably going to take around 6 hours for this. Let's give us a couple of hours of preheat so I don't explode my pottery in there. Turn that down to 4 and go. This was smoking a bunch, so I opened the lid a crack to let air in and burn away the vapors from the bones. I thought that since I'm producing a lot of heat, I might as well stack some blocks around it and make use of it. Made me a little pizza oven on top of my kiln. Okay, so this finished cooking. I let it cool down overnight. Let's see what we got. So the sulfide ore is now turned red. Might have had some organics that burned off. The limestone one appears to be well cooked. And these, the test samples I was doing, it's like that one worked, that one's good. those two. I'm probably gonna have to reheat and adjust the recipe or try again. See, that's why I did that test. So I am only doing it on a small scale rather than a full crucible worth of material. The bones look pretty good though. Yep, those will grind up just fine. Remember, we started with 60 grams. Now it's 41. The difference, mostly, is CO2 in the case of this sample. So now that the samples have been roasted to remove volatiles and thoroughly oxidize them, the next step is to combine them with something to make them fuse or melt and become liquidy at temperatures that we can achieve. And to do that, I need to make a flux. The main component of the flux is going to be sodium carbonate. In this case, I'm using washing soda bought from the store. You could also use baking soda. And some borax, which is also purchased from the store. The problem with these is they're both hydrated, or in the case of baking soda, if you go that route, it's got a lot of extra carbon dioxide. And just like the carbonate sample that we had, those water and carbon dioxide, if that bubbles out during the assay process, it's going to cause the sample to boil over and you're going to lose it. So I'm going to preempt that by heating the washing soda and borax up to about 600 degrees Celsius to remove all the water and carbon dioxide. I don't really want to fill the crucibles all the way up because the borax especially is going to expand as it cooks. Another reason we want to do this now so it doesn't expand later. Now the other main component of the flux is going to be silicon dioxide or silica. One of my rock samples already has a lot of that, so won't need it. The other two will. And for that I can use a lot of things. I could use fine sand, which I've used a lot in the past, or even ground up glass. But today I'm going to be using some diatomaceous earth. It's in a fine powder and is nearly pure silica. This does contain a lot of water though, and just like I'm doing here, the water has to be removed, not only to prevent it from being removed later and causing a boil over, but also to make weighing more accurate, so I've not got the water weight. I do have some of this inside the furnace already. It's actually cooling down as I speak. This here that I was using to pack around one of the test samples, this is diatomaceous earth. Didn't get contaminated, and it's certainly dry now, so let's bag this up and use it as our silica source. You can tell that I'm filming this out of order. Now you might have noticed this pink stuff here. This is 60 ground up Pepto-Bismol pills. And that is approximately 15 grams worth of bismuth. And that is going to be used as the collector for pulling those precious metal particles together and bringing them down to the bottom of my container. Now, the reason I'm cooking this here is, first of all, to remove volatiles again, but also the bismuth subsilicate, I hope I say that right, contains a lot of carbon. This stuff also has a lot of starch and other binders which contain carbon as well. Now, we do need some carbon to react with the bismuth to reduce it to metallic form, but the amount that's in here is just too much. You can still get away with it if you cook the sample for a really long time and wait for that carbon to float to the top and burn off in the oxygen of the air. But until that carbon all burns off, the sample will be very thick, it won't release the metal particles, and it just doesn't behave well. So it's much better to roast it beforehand to completely oxidize everything and then add the amount of carbon you need later. Okay, so hopefully I've explained everything. Let's Put the lid on here, and I'm gonna turn this on and cook her up to about 600 degrees Celsius, very slowly. Oh, the drones are flying. Very nice. Let's crack this open and see how it did. Give that a bit of a stir. And it looks like it's completely oxidized. Okay. Things have cooled down. So before it absorbs moisture from the air, I'm going to break it up and then transfer it into a plastic bag. So here's all the chemicals, got my notes handy, and here's the sample. Now you'll notice I've kept it inside of a plastic bag to keep air from getting to it. Although with the silica, it doesn't really matter. Anyway, I'm going to weigh out half of the sample. That way I've got enough to try again if I have a failure. And also my crucibles that I made are really only big enough for a smaller sample anyway. There we go. So there's 30 grams of the silicate ore. Now this is essentially pure silicon dioxide. So to this, I'm going to add an equal mass, so another 30 grams of the sodium carbonate. Try to kind of grind it up as it's being added. If there's some lumps, it doesn't really matter a whole lot. They'll melt. Soda ash. Now for the borax, I'm just going to do a little bit of borax. This isn't even really needed, it just makes the mixture more fluid. It will cause damage to the crucible, so you want to use a small amount. Certainly a lot lighter now that I've removed the water. Okay, that's probably plenty for the silica. Now for the bismuth that we roasted, I'm going to add all 15 grams. Of the bismuth. Oh, you little schnack. Okay, not a big deal. We don't need any of the diatoms. We don't need any more silica. There's plenty there. So to reduce the bismuth, I'm going to use some cornstarch. That should take roughly 2 grams. Slight excess is fine. So there's the assay charge. Get that mixed up. I'm actually going to transfer it temporarily into this plastic bag just to make mixing easier. Don't want to lose any here. Crush up those lumps as well. Okay, so now I've got this that I'm trying out. It's a crucible within a crucible, or a lined crucible. If the inner liner breaks, the outer one will catch it. The inner part I made, this external part is commercial. I've never used it for precious metals. I just melted salt in it once, so it should be good. Okay. It's about as full as I'd want it to be. Now all that's left is to cap it with a little bit of boric acid. The boric acid melts at a low temperature and will seal the mixture from the atmosphere before it gets really too hot. There we go. So here's the carbonate ore. I'm going to weigh out 20 grams. So this represents the original 30 grams of ore. But of course, we removed a lot of carbon dioxide from it. But this is just as well, because the carbonate is a lot harder, or the lime is a lot harder to fuse. Perfect. All right, let's get this out of the way. For this one, we're definitely going to need the silica. In fact, I'm going to weigh out 20 grams, so pretty much the whole weight of the sample. There's 20 grams. It'll pack down. Add that to my ore sample. I'm going to do another 20 grams of the soda ash. Actually, let's go up to 25. A little bit more. There we go. Let's do some borax. 4 grams seems about right. It's roughly a quarter of the weight of the silicon, from what I've found. My testing works. And of course, same as before, 2 grams of starch and 15 grams of bismuth, or however much oxide that takes to get that much bismuth. There's my starch. That comes out to 17 grams of the bismuth oxide. That in there. And give it a stir. A good mix. I just started the camera. I just weighed out a sample that's half, just like the other ones. Now the host rock for this ore looked like mudstone, which means it's going to have a lot of alumina in it. And that means I'm going to need more borax than I did for the other ones. Did roughly a third of the weight of the original sample. So that means almost 10 grams. Yeah, that should do. I need another 10 grams of the diatomaceous earth. 30 grams of sodium carbonate. Okay. $16 grams of bismuth oxide, just like before. What was it, 17 grams. Now, for my testing, I discovered that I needed more starch. More than the 2 grams. So I'm going to go up to 3 or maybe even 4 to counteract the iron oxidizing it. There we are. Okay, get that mixed up and put it in a crucible. Hopefully it's big enough. Okay, there they are in the little furnace. Come on, no boilovers. Let's only go medium. You do want to kind of heat it fast so that too much of the starch doesn't burn away. But also you don't want to go too quickly, otherwise things might boil over. Okay, so it's hot enough. All the starch should be converted to charcoal by now. Let's have a peek in here. Looks like it's pushed up a little, but it's not necessarily boiling over, so I think that's good. You can crank that up now. The furnace has reached a temperature in excess of 1800 Fahrenheit, or 1000 Celsius. The crucibles are no longer bubbling. There's no pieces of metal floating on top or anything. It just looks like little cups full of honey. So that means that this is done. I'll just open the top of the furnace, shut it off, let everything cool. Well, everything's had a chance to thoroughly cool down. That one looks really good. Complete fusion, it's laid flat. Which one is that? That's the sulfide ore. Dark color is probably from the iron. The silicate ore did pretty good also. Can I get the liner out? I can. Oh, great. What is that? A piece of clay? Okay. And the carbonate one. The one that was giving me trouble. Yeah, looks like we had a bit of a boil over. Fusion is incomplete. I would redo this one. Adjust the recipe a little. I think for the sake of this video, I'm just gonna roll with it. I'm sure. It's stuck up there. Well, let's bust them open. Let's see what we got. Let's see if I can separate it from the dish. Not too hard. See if we got a bead of metal in there. Yeah, there's metal. Now the bismuth you have to be kind of careful with because bismuth breaks. Lead will flatten if you hit it, but bismuth shatters. Yeah, see, it fused, just not completely. There's some undissolved bits in there. It's sure hard. There we go. Okay, well, we can clean that up. Yeah, see, that's much better. This is more like glass. Actually, it is a kind of glass. Okay, so my bead is a little small, but that will work. That separated real well. That's great. That'll do. And the sulfide ore. Yeah, it's a shame to break the crucibles, but I really can't reuse them. So even if I poured this out, I'd still be out of crucible. So I find it's better just to let it cool inside the crucible. chunk of obsidian. Ah, yeah. That's perfect. Yeah, that's the right size. Cool. I'll just clean these up. Okay, there we go. The bismuth is harder than the lead, so in some ways it's easier to get the slag off. You definitely want to get it all off because any bits of slag will really mess with the cupellation. There it is. So here's the beads all cleaned off, no more slag. The number 2, the one we used extra starch on, weighs 10 grams, the other 2 weigh 5. So I think I could have even gotten away with more starch. Because there's about 5 grams of bismuth missing here on this one and 10 grams for these 2. The cupels, which I'll be using here, you can see I've marked them so you can tell which is which. I'm now going to place down into the furnace. I'm going to heat them up to glowing red hot before I add the metal beads, because right now they might contain a little bit of moisture, and that moisture needs to boil off before I add the metal, otherwise it'll cause it to splatter all over the place. So let's get the furnace going again. Okay, should be up to temperature. Slide off the top and unload the metal beads. Make sure I get the right bead and the right cupel. Seal her back up. I have a little hole that I can watch them. The camera doesn't do so well. Okay. So it's gone a while. Looks like it's done. Just let them cool now. Looks like I got them a little bit too hot. You do want to kind of heat them only enough to oxidize and get the metal to go off. Any hotter just damages the cupel and causes it to crack, but looks like I got away with it for now. Turn off the furnace. Alright, let's see what we got. I'm not seeing a bead. This one here just looks like it's got a piece of the furnace that fell in. Yeah, no metal there. It's kind of sparkly there, but that's just some of the recrystallized oxide. That's a little depressing. I don't have anything to measure with my calipers. I guess that means wasn't enough here to really speak about. And now I know. Hope you enjoyed. I'll see you next time. Alright everyone, editing Cody here. So as you can see, I'm currently underneath the greenhouse at Chicken Hole. This is the coolest spot on the property I could find. It's 95 degrees today. Way too early in the year for this kind of heat. But anyway, after editing this video with the power of hindsight, I've decided that I kind of made some mistakes and I probably should redo this project. I probably won't publish this publicly. I'll just have this for the Patreons. The problem is I had 2 unknowns, and that's a big no-no in science. You see, I'm kind of new to using bismuth, and I'm very rusty in fire assays in general. Like I used to use lead, but like when I was seriously doing it was over 10 years ago now. So and adapting it for bismuth. You know, maybe I've made a mistake somewhere. Maybe I didn't get the precious metals because there was an issue. I'm sure there is some issues, at least. So maybe I made a mistake and I didn't find the precious metals. Or maybe the samples I used, the rock samples, just were unlucky and didn't have anything, right? I can't say for certain which of those is which. Maybe it's a combination of both. So I need to redo this project, or at least off camera do some testing on my own with samples that I know what is in them. Maybe even something that I've added the precious metals to, just to make sure I'm able to get it all out, right? So there we go. I've got some more work to do. It's kind of upsetting because I spent so much time on this video and now I've got nothing to post on my YouTube channel. But I'll just carry on. I'll start working on the next chicken hole base episode, I guess. In the meantime, I did film some more making the cupels and making the crucibles. So I'll just add that in the end. So hope you enjoy. Now to make the cupels, I'm going to start with the charred bones and channel my inner beanstalk giant. Basically, I'm going to grind them into a very fine powder, roughly the consistency of flour. You know, come to think of it, a flour mill might actually work pretty good for this. Okay, that looks fine enough. Essentially bone flour now, or bone ash flour. So now what I'm going to do is add just a little bit of water. You don't want to make a dough, you just want to make it so that it'll stick together. Okay, this is about right. You want it just wet enough that it'll clump together and hold shape, but dry enough that it's still crumbly. Okay. So now I've got this piece of pipe here, which I'm going to loosely pack the crumbled bone dough into, like this. Okay. Now I'm going to bring it over to an anvil and press it using this piece of wood which I've carved into the shape of the top of a cupel. So kind of a round shape with a lip on the edge. So kind of pack that in good. Give it a few whacks with a mallet. Try to keep it straight. Push it out. And then carefully unstick it from the wood. Twist it off. There we go. There's the finished cupel. All it needs now is to dry, which could take several days. Of course, make some more. Now for the crucibles, I'm going to use a mixture of ordinary pottery clay, just some low-fire clay that I bought from the craft store, and a roughly equal volume of fine silica sand. Okay, add a little bit of water and get these mixed together. The sand, silica doesn't expand as much as the clay does when it's heated, and so it helps it with thermal shock. Also, the sand provides channels for gases to escape during firing, so it's more resistant to moisture. The sand does make the crucible less strong against the flux, though, because the sand is easily dissolved by the flux. So the more sand you add, the less likely the crucible is to withstand being used. But since I tend to use my crucibles only once, you can go with quite a lot of sand here. 50% or perhaps even a little more. If you plan on reusing your crucibles, you might want to use a grog or ground up clay that's already been fired. That would provide some of the same benefits, but not be susceptible to being dissolved by the flux. Okay. I'll just get this finished incorporating. Okay. Now that I've got it all incorporated, you can wedge it like you would do to remove air bubbles, just like you do any other form of pottery. And as for the actual crucibles, I've been doing just like a pinch pot, essentially. You probably could also use a potter's wheel for this. In fact, I think I'm going to buy a potter's wheel just so I can produce crucibles that are more uniform. You want to kind of have the bottom thicker than the top. Up here at the top, it doesn't really matter. That can go pretty thin because it's just to keep the material from overflowing. Down at the bottom, it's got to resist being dissolved by the flux. So it's got to be thicker because that's where it's going to be encountering the flux for the longest. Okay. Flatten the bottom. You do kind of want a spot at the bottom of the crucible where the heavy stuff can collect. And that's roughly all you need. You can of course do any shape you like. Flat dishes to put underneath the crucibles to catch overflows, etc. Just make sure it's completely dry before you put it in the furnace. In fact, I would recommend firing it like any other form of pottery before using it as a crucible, because I'd much rather it explode empty in an empty furnace than with a full charge of flux. You know, if there was a little bit of moisture that built up and it did explode, that'd make a mess. There we go. Crucible.